Welcome to Spring LIB.
For the following systems of equations, let's calculate the cell potential after the addition of 15 moles of ammonia. Let's first start by creating a redox reaction. So we get the reduction of silver, the E0 reduction here, it's 0.80 volts. We have the oxidation of cadmium. E0 oxidation here is positive 0.40 volts. Multiply the reduction half reaction by 2, so we can cancel out the electrons, and we'll get 2Ag plus, cadmium solid, 2Ag solid, cadmium 2 plus, E0 cell is equal to 1.20 volts. Now let's create our equilibrium here. Ag plus at NH3 in equilibrium with AgNH3. K1 here is equal to 2.1 times 10 to the 3. And we'll have AgNH3 at NH3 in equilibrium with AgNH32. K2 here is equal to 8.2 times 10 to the 3. Combine these two together. Ag and H3 would cancel. We would get Ag plus 2NH3 equilibrium with Ag and H32 aqueous. Equilibrium constant here is equal to K1 times K2. This is equal to 2.1 times 10 to the 3 times 8.2 times 10 to the 3. And the equilibrium constant here works out to 1.7 times 10 to the 7. That's quite a large equilibrium constant. So because the value of K is large, the reaction goes to completion and the backwards reaction takes place. So reaction or equilibrium here is Ag plus 2NH3 in equilibrium with Ag NH32. Before the reaction, we have 1 molar Ag plus, the addition of 15, this is in 1 liter, so 15 moles per 1 liter is 15 molar, 0. After, we're going to go to completion here. Our final value here will be 0. 13.0 and 1.00. Then we'll have our change, the backwards reaction, minus x plus 2x and x, and at equilibrium we'd have x, 13.0 plus 2x, and 1.00 minus x. Our equilibrium constant here is equal to Ag NH32 over the concentration of Ag plus NH3 squared. Let's plug in our values here. The equilibrium constant, 1.7 times 10 to the 7, we calculated previously. 1.00 minus x, 13.0 plus 2x, and we're going to assume the change in x is negligible. And therefore, this equation becomes 1.7 times 10 to the 7 is equal to 1.00 x 13.0. Solving for x, we find that this is equal to 3.5 times 10 to the negative 10. Therefore, going back to our ice table, the molarity of Ag plus is equal to 3.5 times 10 to the minus 10. Now we'll calculate the equilibrium constant based on our redox reaction. This will be the concentration of cadmium 2 plus over the concentration of Ag plus squared. This is equal to, cadmium was 1.0. This is 3.5 times 10 to the minus 10 squared, and we get 8.16 times 10 to the minus 18, or 10 to the positive 18. And then, to calculate the cell potential, E is equal to E naught cell minus 0.5 0.0591 over n log of k. E naught cell value is 1.20. 0.0591. N is the number of electrons involved in the redox reaction, which is 2, log of our equilibrium constant, which is 8.16 times 10 to the 18. And this would give me a cell potential of 0.64 volts.